So by far our longest unit all year was the triangles unit at the beginning, pretty much the entire month of January and into February before we finally tested. If you watch the semester review, we kind of broke it um, into four main stages, and those stages were, Pythagorean theorem plus primitives. We had special right triangles. We had SOHCA, which I think you'd call right triangle trigonometry, basically. And then finally, we had the laws of sines and cosines. So those were the formulas that worked on all triangles, not just the right triangles. They worked on oblique triangles also, which are non-right triangles, right? So that's what we did during that first 5 weeks. And here are some answers for you. Um, Kind of flip through. If you need to pause them, you can. Looks like we have the work down here for number one. We Nope, I guess that's the work for number two. So we multiplied the 3 and the 4. We multiplied the root by the root, which turned out to be a perfect square. So that's where the 72 came from. Number 3 was just a Pythagorean theorem problem. Technically, it was a primitive, but probably one of the bigger ones. Number 4 was looking for which set of numbers worked in the Pythagorean theorem, and it looked like C actually did work. Number 5 was a special right triangle problem, 30, 60, 90 triangle. And so if they gave us the long leg, we would have to divide by root 3 to get to the short leg, which would give us 9, and then multiply by 2 to get to the hypotenuse, which would be 18. Number 6 was the distance formula, and the distance formula really is just the Pythagorean theorem, but we see the work down here. We plug x minus x in and y minus y in, and you can see how we ended up with the square root of 442, which happily for us turned out to be a perfect square, 21. And then finally, a multiple of the 345 primitive. We're just looking for a set of three numbers where the 3, the 4, and the 5 are all multiplied by the same thing. A lot of times people get confused by C on this one because it's 3 squared, 4 squared, 5 squared, but that's not how primitives work. Primitives are where your set is all multiplied by the same number, like 3 times 4, 4 times 4, 5 times 4, which is where B came from. All right, part 2 was some right triangle Pythagorean theorem problems. You can see number 1, the answers on a multiple choice or multiple select type question will either be approximations or an exact value, so you won't have to decide which one to do. It'll be there in one way or the other. Same thing with number 2. It doesn't look like the work for number 2 is there, but if anybody had a question on any of these that aren't fully worked out, you can let me know. By the way, number 2 is a 30, 60, 90 triangle because it's a right triangle, and notice that one of the legs is exactly half the hypotenuse, and that's only going to happen if it's 30, 60, 90. Number 3, students will often struggle on problems like number 3 because they're just not sure how to deal with 3 root 2 as a number. And quite frankly, you just deal with it like a regular number. You just have to remember you got to square both parts, right? 3 times 2, 3 squared, I should say, is 9, and root 2 squared is 2. And then you just get an 18 out of that, right? So not a big deal. You just put the numbers in. Make sure you recognize the hypotenuse. The hypotenuse always across from the right triangle, right? Number 4 turned out to be a rather large primitive, 12, 35, 37, probably one you wouldn't know, but you don't need to know them when the Pythagorean theorem will solve them for us. The last two. Notice number 6 could be done very quickly using primitives. Once I noticed that 30 and 24 are both divisible by 6, leaving the numbers 4 and 5. That's got to be a multiple of 3, 4, 5. And sure enough, 3 times 6 is 18. So primitives will save you time. Now, part 3 was on special right triangles. So to get from the hypotenuse to the short leg, I'm going to divide by 2. And then from the short leg to the long leg, I'm going to multiply by root 3. Number 2 is an isosceles, right? That makes it a 45, 45, 90, which means to get from the hypotenuse to the leg, I'm going to divide by root 2. Notice you can't divide whole numbers by roots. And so this is where we have to remember how to rationalize to get that root off the bottom. You will not see 16 divided by root 2 as a final answer. You got to be able to rationalize them. On this one, we're going to multiply by root 2 to get to the hypotenuse, and sure enough, 13 root 2 is the answer. Number 4, we need to double it to get to the hypotenuse, right? Short leg times 2 for the hypotenuse, so that's going to be 16 root 2. And the long leg has to be multiplied by root 3. Now notice, you can't multiply a whole number by a root, but root 2 times root 3, a root times a root is a root. That's where this root 6 comes from right there, okay? Another 30, 60, 90. So we're going to divide by 2 to get the short leg, 11 root 2, or 11 root 6 for the short leg, and then multiply 11 root 6 by root 3 to get the long leg, which, by the way, think about that. 11 root 6 multiplied by root 3 is going to be 11 root 18. The root 18 can break into a root 9 times a root 2. So really we get 11 times 3 root 2, and that's where the 33, oops, that should be a 2 there. That's where the 33 root 2 comes from right there. Here's a combination problem where we had to multiply by root 2 to get to the hypotenuse of the smaller 45, 45, 90. So that's 4 times root 2 times root 2, which is just 4 times 2, so this was 8. And multiply that by root 2 to get to the hypotenuse there, so 8 root 2 for x, and then isosceles, right? So those are the same for y. Number 7, another combination problem. So started with a 30, 60, 90. So we had to divide by 2 to get to the short leg. 9 root 3 times root 3. Think about that. 9 root 3 times root 3. So that's just going to be 9 times 3. That's where the 27 comes from. In the smaller 30, 60, 90 triangle, we have the long leg, so we divide by root 3 to get x. Well, that just means the root 3's cancel. So x is 9, double that to get to the hypotenuse of the smaller right triangle. Here is what I'm talking about, right? Smaller 30, 60, 90. 9 times 2 is 18. That's where that comes from. Number 8, another combination. Divide root 60 by root 2, which means we're going to have a little rationalizing to do here. But once we know the short leg is 30 root 2, I double it to get the hypotenuse, and I multiply by root 3 to get the long leg of the larger 30, 60, 90 there over on the left side. And finally, number 9, I should say. Number 9 was a problem very similar to a problem on quiz number 1 from January. If you go back and check that out, you will have seen that it started off with a couple problems that were a couple triangles that were not special right triangles. We do not see 1 to 2 relationship between these sides. We do not see any 30s or 60s or 45s listed in any of these problems. If it's not a 30, 60, 90 or 45, 45, 90, do not use special right triangle relationships. It's not going to help you. This is just a 5, 12, 13 primitive, so P just came right out of that. And then 9 squared plus 12 squared is going to give you 15 squared. That's where we get Q. Actually, it's a 3, 4, 5 multiplied by 3, so it's a primitive. Now we finally get into a 30, 60, 90 right triangle here. so we're going to divide the long leg by root 3. That's the rationalizing you see right here to get 5 root 3, double that to get 10 root 3. And then now I'm in this 45, 45, 90, and I can multiply 10 root 3 by 2, root 2, to get 10 root 6 for S. So don't always use special right triangles, because every triangle is certainly not a special right triangle. Right, part 4 was distance formula, where you could, if it's a small distance, build a right triangle out of your points, and then just use the quadratic, the Pythagorean theorem. That's what we did, right here. But you could also plug the points in, which is the safer way, to the distance formula. Now, as you can see with letter B, these points are way too far apart. I don't want to draw a huge, massive triangle. So I'm going to plug those points in down here and let the distance formula take care of the work for me. Okay, I do not have the work, I don't believe, for part C, but if you are unable to make that calculation, let me know. Otherwise, this is a really good example of the kinds of work to get through those types of problems. We got into SOHCA for parts 5, 6, and 7. Just a little definition, multiple choice for 1, 2, and 3, right? Opposite over adjacent is tangent. Opposite over hypotenuse is sine, and adjacent over hypotenuse would make the cosine. The problems 1 through 6 were just calculator problems. You did have to remember on problems 4, 5, and 6 to use the inverse sine, cosine, and tangent functions to undo the sine, cosine, and tangent and solve for the angles. Part 7 was knowing the laws of sines and cosines. Okay, you only need to know one law of cosines. I would only know this first, this first chunk. But notice it can be rewritten with any angle, side, opposite combination. As long as you remember that A, B, and C are generic placeholders, you really don't have to worry about knowing all 3 cases there. You really just need to know the one primary case. The first, I think, 4 of the problems in part 8 were right triangles, so you just use SOHCA. Number 1 was a tangent problem. I'll just kind of scroll through here. If you want to pause the video at any point in time to take a longer look, you can do that. Remember, when you're solving for an angle, like in this case, you've got to take the inverse cosine. Number 4 is an example where you could solve for the height the long way by making a little right triangle and setting up a little sine equation. But if you remember that 1/2 AB sine C shortcut formula, then all you have to do is plug the angle on the 2 sides around them in SAS, and you get it very, very quickly for the answer. Okay. Now, once we got to the last set of problems, they were not right triangles anymore. So we had to decide whether to use a law of sines or cosines. And the trick really is, if you can find an angle and a side that are across from each other, you should be able to use the law of sines, which is an easier formula. And I'll let you kind of look at number 5. And then here is the work for number 6. Notice this little display just reminds us the 3 cases for law of sines, the 2 cases for law of cosines. The actual 6th case is AAA, but you can't use that because unless you're given one side length, you have no scale. You have no way of knowing the lengths of any of the sides. And here's the last 2 from that set. Notice here I have an angle and a side that are across from each other. And that's going to tell me I can use the law of sines. Notice that on number 8, I do not. The only angle I have is 44, which is across from a side I do not know. That's going to tell me I have to use the law of cosines. Make sure that this angle is going to be across from the side that has to go in as the isolated side, the c squared in our formula. Okay. And once again, one last look at when to use law of sines, when to use law of cosines. You should have a notes page that does have a lot of that information on it. The last set was some application problems. They were all based on right triangles, though, so they should have been just SOHCA problems. Okay. And that's kind of what number one would have looked like if you set it up. Number two. And remember, you can always use the opposite adjacent, or I'm sorry, alternate interior, opposite interior or alternate interior angles on problems that have angles of elevation and depression. Okay, so if this was an angle of depression problem, you could have turned it into an angle of elevation problem because of the alternate interior relationship there. And here's the last one. So hopefully this helps you check your answers and maybe see what some mistakes might have been for you. If not, then you know, we're gonna have some help sessions, and you know, all I can say is be there. If you have questions and you're not understanding things, then you gotta be there. That's all. It's the only way you're gonna fix things. Okay. Let me know. Area comes next. Adios.